This video is about using metaphor to compute basic confidence and prediction intervals. So we're going to get confidence intervals for the random effects variance component and for I squared, and we're going to get prediction or credibility intervals for the mean. Typically in psychology, just get confidence interval for the mean, but the random effects variance component is very important in meta-analysis because it indicates the variability in true or underlying infinite sample effect sizes. And also, it's oftentimes poorly estimated and it has an impact on the weights and thus the overall mean estimate when you do a random effects analysis. So it's important to know how much uncertainty is associated with this estimate. And I squared is an estimate of proportion of variability due to between studies variance. So it's not sampling variance, it's the other kind of variance. And this I squared is analogous to R square in regression, where in the meta-analysis, I square is the proportion of variance observed that's due to real or true or infinite sample effect sizes, or it's the proportion of variance due to random effects. This also is an important thing to know, and we want to know how much uncertainty there is about this estimate. We also get a mean, and the printout gives us a confidence interval around that mean, but when the random effects variance is greater than 0, then the overall mean is in a sense quite informative, but in another sense it's rather misleading because the true or underlying effect sizes vary. There's a distribution of those things, and we want to know where that distribution is. So the prediction or credibility interval creates a range, a series of values, a band that has ends that are supposed to contain a percentage, and typically it's a 95% of the true effect sizes, the underlying effect sizes. And this is usually based on the assumption that the distribution is normal. So you can ask for metaphors, prediction, or credibility intervals, and it will use the Z and give you a 95% confidence interval for the normal. If you want the Higgins intervals, those use the T distribution instead of Z. And if you have a lot of effect sizes, it won't make any difference. But when you have small numbers of studies, small numbers of effect sizes, then you probably are underestimating the REVC because of the small number of studies. So if you want to account for that, then you can use the Higgins method. And I've created some code that will do this for you because metaphor doesn't. Okay, so here's what Higgins prediction interval looks like. You go up and down from the mean, approximately 2, and then this is the standard error that you want to use, and it's got tau squared and the variance of the mean in it. And if you use Z, of course, this becomes 1.96, and T changes, it goes up and down depending on, usually we want 95%, but you can change that, and the degrees of freedom are typically K minus 2, where K is the number of studies. And here's a reference if you want to read more about it. So I'm going to show you our code for 2 studies. I've showed you the McNatt data before. This is the Pygmalion studies in organizations, and then I'm going to show you the McDaniel data where he's got predictive validity for interviews and predicting job performance. So let's take a look at R, and I have written some script to do this, and I'm first going to load things up. Alright, so R begins working, and we've got the metaphor awakened, and we've got the XLSS X awakened so that we can read data. And here I've got the Higgins function, and so you're going to need the mean from the meta-analysis. You're going to need tau squared, you're going to need the standard error of the mean, and K the number of studies. So this will compute the Higgins prediction interval for you. And I'm now going to load some data and run an analysis, and we'll talk about that. So we've read in the McNatt data here, and I've asked it to print out. So here we have the studies, the names, their effect size is D, and their variance is V. So we're going to do a generic meta-analysis. Okay, RMA, so D and V. We're going to use the Dersimonian and Laird method and McNatt dat. We ask R to print the results, and it complies. And we see we've got 17 studies. Dersimonian and Laird estimator. Tau is 68, tau squared is 4643. Our overall estimate is 1.09. Here's our standard error. Here's our lower bound and upper bound confidence interval for our grand mean. So to get the confidence intervals, the additional confidence intervals, I say confint and then McNatt results, which is the results of running metaphor. And I now have estimate of tau square, and you can see it's this same estimate, but now I've got confidence intervals for that value. Tau, you can see that's the same estimate. I've now got estimates for that value, and you can see this is a rather wide interval for tau. Here's I squared, and you can see that's that estimate, and it goes from about 90 to about 98 here. So that's not quite as bad. You can see, no matter what, it's rather heterogeneous. We've got a big value of tau, though we don't know exactly what that is. We have a big value of I squared, even though we don't know exactly what that is. The prediction interval we get from a metaphor has, here's our value, here's our standard error, here's the lower bound and upper bound. These are the same as the value in standard errors here, and the same as the lower and upper bound. But now we've got the prediction interval or credibility interval that is based on Z, and it goes from minus 29 to about almost 2.5. So you can see this is really quite a very large range in which the true effect sizes D might fall. And that's based on the 1.96 or the Z distribution for 95%, and a similar distribution based on T instead of Z with 17 studies gives us a lower bound of minus 41 and upper bound of 2.5, of 2.6 about. And you notice that this is actually a good bit wider than the metaphor estimate, and that's because we have 15 degrees of freedom, so our value of T is going to be bigger than our value of Z, and that shows up here. I want to show you the results for the McDaniel data, so let's compute that. Built-in data set from metaphor dat.mcdaniel 1994, and these are correlations between job performance is the dependent variable, and the independent variable is scores on a interview, a personnel selection interview. So here are the studies, and we come down and I say I want metaphor to analyze. Here's the number input, here's the correlation coefficient. We're going to use Dersimonian and Laird. We're going to analyze the Fisher transformed correlation, and we're going to analyze McDaniel 1994. And it does, and I ask it to print, and it says, okay, we have 160 studies. We're going to use Dersimonian and Laird. We have tau estimate is 1636. Tau squared is 0268. Our overall mean is 2368. Our standard error is 0164. And our confidence intervals go from 2046 to 2690. So to get the additional confidence intervals, I say confint McDaniel res 1. And we've got a confidence interval for tau squared and for tau. So this goes from, this is 1636, and it goes from 1549 to 2240. So this is a tighter confidence interval. We have more studies. Notice that it's not exactly symmetrical, which is to be expected because tau is not going to be symmetrical. and I-square is about 0.8, and it goes from about 78 to 88. Okay, so that tells us where our likely values of tau and I-square are, and prediction interval, we've got the value just like we did here, and we've got the confidence intervals just like this. And in this case, the credibility values go from about minus 0.08 to 5590. So here again, it's wider because of this value of tau. And if you want the Higgins intervals, you just plug in the numbers from meta-analysis here. Again, I had to do these. You would have to plug them in from your own meta-analysis. And it gives me the Higgins prediction interval goes from minus 0.88 to plus 0.5617. And you notice that these are quite close to the values that come out of metaphor, and that's not surprising because in this case we have 160 studies, so we have 158 degrees of freedom, and Z and T are almost the same. So I would say if you are doing these kinds of prediction intervals and you have a small number of studies, say 100 or less, it's probably worth your while to ask for the Higgins prediction intervals. And that's it for this module.